So now let's proceed to really understand how we can use the dynamic programming to solve the problem, right? So just recall that our destination is always t, right? This is the problem, and I want to be able to, at the end of the day, for any v, I'm able to tell the shortest path between from v to t, right? So we are also working on a simplified setting, where we have no negative cycle, right? So these are the setup, right? So now again, I have been repeating this message multiple times. If I want to find a DP solution, basically the step one, it is what, right? So it is that we want to find we want to define the subproblem and find the recursive structure. Recursive structure. And then step two is really just that I want to memorize the subproblem, the problems we have computed, right? So it's, again, there are two steps, right? So we have been using the same function again and again and again to really to define the problem we are interested in, right? So here it is the opt I and v, and the definition here is that we want to find the length of the shortest path connecting from v to t that uses at most I edges, right? So this kind of shortest path for the dynamic programming problem, it's a bit different from what we have seen, right? What we have seen, right? If you look at the sequencing problem we just saw just now, we have x1 up to xi, y1 up to ij, right? Of course, like intuitively, we really just want to line up the two variables in the two-dimensional manner, right? So if you look at the next set, right? Next set problem, right? It's really just that also it's giving us a strong hint it's a two-dimensional problem because there's a capacity variable and there's a value variable, right? So it's a two-dimensional. Right. For this problem, we actually have to be a bit creative, right? We know we want to solve the shortest path between t and v and t, but then we sort of want to introduce this extra variable, right? Controlling variable. This is really, you have to think. Basically, this variable is introduced out of the blue, right? So it's not as intuitive as the sequencing problem or the knapsack problem. It's obvious that we know it's a two-dimensional problem, right? So this one, then we sort of need to add this extra variable. With this extra variable, the combinatorial structure of the shortest path all of a sudden becomes very clear, right? So this I here, so let me just repeat the opt IV basically is really just among all the passes connecting from V to T that uses less than I edges, right? So we have to force that it uses less than I edges, and among all these passes, what's the optimum solution, right? So now at the end of the day, if I want to compute v to the shortest path from v to t, I just need to compute the opt n-1 to v. Why is that? Why do we need at most n-1 edges? That's the reason that we assume that the path is simple, right? It has no negative cycle. When it has no negative cycle, we have shown that in the previous lemma that there always exists a shortest path that is simple, right? So let me just erase this one. So this is the key, right? There's always exists a shortest path that's simple, right? So that's the reason that in case we are guaranteed that the solution, the input that doesn't contain any negative cycle, we know that we don't need to look for any passes or passes that has length larger than n, doesn't need to be considered at all, right? So that's the reason that our dynamic programming needs to add an n at n-1 level, right? So now let's really just think about how can we build up recursive for this for this subproblem, right? So we sort of want to solve the optimal solution of the optimum solutions of IV, right? The shortest path between between u to v, v to t that uses less than I edges, right? So again, we consider the different possible cases for the optimum solution. The first case is really just that although we require the path that doesn't need more than I edges. In fact, the optimal solution doesn't need more than I minus 1 edges, right? It's really just that it's not necessarily true that the optimal solution for this problem has exactly I edges. It can also be that the optimal solution has less than I edges, right? For this case, right, so it's this pretty simple recursive. We just look into the opt I minus 1 or v or v, right? And in the second case, right? So in case that in case the case 1 is false, then basically we can conclude that the shortest path uses exactly I edges, right? So basically in this case we sort of know that v and from v to t that if I want to solve the opt we want to solve the opt I and I am, so let me just delete this one, right? So if I want to solve the opt I and v, and I sort of know that we are in the case 2, then I know that I exactly need to use I edges, right? So these are the I edges, right? So now I sort of want to understand that what's my next hop, right? My next hop, let's say this is w, right? So if my next hop is w, then sort of what we can see that where can we find the path between w and t, right? The path between w and t is basically we sort of recurse, right? So the total number of edges here is I, right? That really just means that the number of edges between w and t, right? So the number of edges connecting from w to t is at most I minus 1, right? So not only that, right? So if I just look at the subpath, right? Just imagine that let's say just that if the optimum path, right? This is the optimum. If this path is the optimum v and t, right? This is sorry. Let me just straight. If this path is optimum I and v, right? Basically that means that this path is among the best path. That has then less than I edges, right? So then we can sort of see that if I just cut off and look at this path, right? Let me just use something that's bigger, right? If I look at this path, this is also going to be optimal, right? In the sense that this path is going to be optimum I minus 1 and w, right? So if I give w I minus 1 edges and then I want to reach t, right? Basically the optimal solution really has to use the same subpath as the optimal solution between v and t, right? So that's the reason we sort of can do a reduction. So in this second case, we can sort of make a guess on what's my next hop. And after I guess what's my next hop, I really just want to solve the optimal solution from w to t. And now I only have budget of I minus 1, right? So this is opt I minus 1 of w. And then as well, I need to add back to there's some weight, the weight cost of between v and w. So this is denoted by LVW, right? So that's the reason that in the second case, right? So we can sort of reduce the optimal solution of v that consists of I steps into a solution that consists of I minus 1 step, right? So I here is really just controlling the size of the problem, right? So when we run the recursive, right, so we have a smaller I. That's sort of suggesting we are looking into a smaller subproblem, right? Right, so that's sort of how the recursive works, right? So at the end of the day, we do have this recursive solution. Basically, you can visually inspect that I build up the solutions layer by layer, right? So each layer would really just be the optimal solution that consists of I edges, right? So I edges, and then this one would be the optimum solution that consists of I plus 1 edges, right? So in case I want to find the optimum solution that consists of I plus 1 edges between v and t, I sort of need to find the optimum solution that consists of I edges between W and T in the previous layer, right? So this is right. So this is right how I visually draw all these things, right? So if I have optimal solution here, and I also have the weight here, then I sort of can concatenate, sort of copy the optimal solution up and then get the optimal solution for the I plus 1 layer. So it's a layered by layered solution structure, and then basically this is also suggesting a way for us to fill in the cache table, right? We really should fill in that from the bottom up approach, right? So we are so the M here, right? Surprisingly, it's the M I is IV, right? Here is the V here is equal to opt IV, right? So V here is really just a node, and the node can be, we can also use the index of the node to represent the second parameter, right? So now we sort of, as this we have been repetitive, right? So it's we are repeating the same technique, like using the cache M to store all the optimal subproblems, right? So after we store all the optimal subproblems, we can just loop. We can loop from I from let I to be from I to 1 to up to n to 1 n minus 1, right? So the looping is from bottom to top, right? After we do the looping, right? So what we are effectively implementing here is really just the recursive relationship we mentioned above, right? Right. This is the first case. And then this is the second case, right? In the second case, actually, we sort of need to make a guess on what is the next hop, and then try to solve the problem, right? And so it's actually not very difficult to come up with the runtime analysis. The runtime is n squared, and the space complexity is m times n, right? So in our notation, it's really just m equal to the number of edges, and n equal to the number of vertices. Right, so this is the solution over here, right? So so there's another thing. So I sort of mentioned that the problem of finding the shortest path it's sort of equivalent to the problem of detecting the negative cycles, right? So I will give you a bit of hints on how the negative cycle can be detected, right? So imagine that this layer is already the layer that's correspond to the opt m minus 1, and the m minus 1 and v for all v, right? So if I continue to run the next layer, right? So it's somehow, we know that if it doesn't have any simple paths, then I only need to run up to n minus 1 layer, right? Because there's no shortest path that has more than n minus 1 edges, right? But in case I continue to run this recursive for one more step, let's run that to find the opt n and v, right? Using exactly the same recursive form. And somehow we realize that this blue plate, right, this blue array is updated. Somewhere somehow we sort of realize the opt n v is different from opt n minus 1 v for some v, right? So it's updated. Some value over here has a different value compared to the one that's in the previous iteration. Then all of a sudden we realize that, well, actually this is basically suggesting that if I want to travel from v to t, and if I want to use n nodes, it's going to be different from using n minus 1 nodes, right? So the only case that's going to happen is that it has exactly n nodes, right? So actually n edges, right? So if there's an update, so this is a high level argument. If there is an update, right, then basically that sort of implies that the number of edges for the optimum solution of mv is going to be n, right? That's exactly going to be n. This also implies the shortest path we have found is not simple. When the only possible scenario in which the the shortest path is not simple, is that it contains a negative cycle, and basically that means that if we really just run one more iteration, then we are able to detect that whether there exists a negative cycle, right? So that's how these two problems are sort of related. Right. So now I think we have sort of wrap up. There are some sort of the low level optimization that we can do in order to solve the problem. But to make this algorithm run faster. But I don't think that's too important. The most important thing is that we are able to come up with a pretty interesting recursive form to solve the shortest path problem with negative weights, right? So here then we sort of wrap up the entire lectures. We are going to cover the news. We are going to cover a few more dynamic